Hi there, and welcome to the lesson on the normal distribution. Again, have your graphing calculators ready because you're going to be having to remember what to press. So if you only watch what I'm doing and not actually do it on the calculator, you won't remember it as well in the exam. So make sure you grab your calculator. Unfortunately, as I'm at home and not at school when I'm doing this recording, the virtual calculator is not working. So all I can offer you when I'm demonstrating how to use it is a little picture of one. So if that's okay, you can still follow what I'm doing. So grab those calculators. So here it is, the normal distribution. So we've got pictures of a normal distribution. So remember, it kind of follows kind of like a bell curve and that kind of thing. So it also can be known as a Gaussian distribution. So here Gauss is back. Okay, let's just go on to it. So let's warm up first, a little review of some earlier stuff. In a class of 25 students, 14 like pizza, 16 like iced coffee, 1 student likes neither, and 6 students like both. One student is randomly selected from the class. What is the probability that the student likes pizza? Okay, so that might seem pretty obvious to you, but regardless, a Venn diagram might still be helpful. So there's 25 students in total, and of the 14 who like pizza, 6 happen to like both. So you could probably still answer this question at this point anyway, because it's pretty obvious. 14 out of 25 is the probability that they like pizza. But still, here's a Venn diagram. So we know that 6 like both when doing these Venn diagrams. Remember, tend to start from the middle and work outwards. So 6 students like both. So because 14 like pizza in total, and that includes the 6 that like both, therefore 14 minus 6, so 8. These two must add up to 14. So 8 out here. A lot of people forget that and put 14 out here instead. But in total, 14 like pizza and 6 like both. And same thing, what do we have? 16 like iced coffee. So therefore 10 like iced coffee only, 8 like pizza only. There's 25 students in total, so check what this adds up to. So we've got 16 plus 8 is 24. It's 25 students in total, so there's 1 on the outside. And here's U because it's representing the universal set. So Venn diagrams are very helpful. So we already discussed what's the probability that they like pizza. So of the 25 students, 14 like pizza. If they said how many like pizza only, then it would be 8 out of 25. But because it's just how many like pizza in general, it's 14 out of 25. So probability that they like pizza is 14 out of 25. And then here's something that might be a bit more complicated. Find the probability that the student likes pizza given that he or she likes iced coffee. So what does the term given that indicate? That's right, given that indicates it's a conditional probability kind of question. So don't forget the formula for conditional probability in your formula booklet. Probability of A, given that B has occurred, so B has to be the thing that is given that, is equal to the probability of the intersection of A and B, and divided by the probability of B. So in this case, it would be the probability that they like pizza, given that they do like iced coffee. So pizza would be P, given that C in this case. So of the 16 who like iced coffee, 6 like pizza. This is one way of looking at it. So the probability of liking pizza, given that they like iced coffee, is 6 out of 16. Sometimes this works, just working it out logically like this, but just be careful. Sometimes you might need to use a conditional probability formula instead, in which case you'd need to do the probability of the intersection of A and B, which intersection is this part here, so that's 6 out of 16, divided by the probability of B. So in this case, it's a probability of iced coffee. So divided by 16 out of 25. So sorry, this was 6 out of 25. So it would be 6 out of 25 for the intersect, divide by 16 out of 25. And 6 over 25 divided by 16 over 25 equals 6 over 25 times 25 over 16, due to the fact that when you divide by a fraction, it's the same as multiplying by its reciprocal. And then the 25s cancel out and you get 6 over 16. This simplifies. So what could you simplify it to? This isn't the final answer. That's right, it would simplify to 3 over 8 is what you should have instead. Okay, so another warm-up. A hospital is trialling a new anesthetic drug, calculator, and has collected data on how long the new and old drugs take before the patient becomes unconscious. They wish to know which drug acts faster and which is more reliable. So the old drug they use, these are the times. So faster would mean shorter time overall. New drug times are here. Prepare a parallel box plot for the data set and use it to compare the two drugs for speed and reliability. So this is going back to old stats. So to do a box plot, you need the max, you need the min, and you also need the median, and you need the upper quartile and the lower quartile. So to do that, don't forget, you would have to work out these 5 things. So you can do that easily on the calculator. You're going to have to watch mine. So you would go, this is how you would enter in for the old drug. The old drug, you would go stat, you'd press stat, you would go across to edit. So go stat, edit, and in L1 you would enter in all these numbers, and then you would go stat, calc, 1 var stats. And then when you scroll down, make sure the frequency list is clear because it's not a frequency table. And you would scroll down and you would find these values. Lower quartile, median, upper quartile, min and max. Then you would do the same thing for the new drug times. You'd go stat, edit, enter the data into L1. So clear the data in L1, go up and clear and enter, and then enter the data in L1, then go stat, calc, 1 var stats, make sure the frequency list is clear, and then press enter and scroll down to find the other values as well. So for the new drug, you would get these kind of values for the upper and lower quartile and median. So you could do parallel box plot. Parallel box plot means on the same axis. So it kind of goes from about 5 up to about 21. So we could go from 0 up to about 25 is what we did. And you have arrows going either way, so you'd have a scale. The median, so the minimum is like a dot. So the minimum is 5 for this one, 7 for the new drug. The maximum is 12 for the new drug and 21 for the old drug. And then the median, so the median is 9, median is 10. And here's the lower quartile, Q1, here's the upper quartile, Q3. Remember to calculate the interquartile range, you could do Q3 minus Q1. So what you can do is you can kind of look at a number of different things. So which drug is more reliable, you can judge by how narrowly spread the data is around the median. So more reliable means kind of they're closer together in value. So you would probably say the new drug is more reliable because one, its range is smaller. The range is the max minus the min. So the range is smaller. On top of that, the interquartile range is smaller. And on top of that, which one is faster would have the shortest time. So the shortest time is faster. So this one, although it's possible, sometimes the old drug was faster. In general, the median value was lower for the new drug. So shorter times mean faster. So using the median, 50% of the time the new drug takes 9 seconds or less, compared with 10 seconds or less for the old drug. We conclude that the new drug is generally a little quicker using the median. The range for the old drug was 16, the interquartile range was Q3 minus Q1 was 4.5, range for the new drug is 5, and the interquartile range was 2. Therefore, the new drug times are less spread out than the old drug times, which are way more spread out. So the new drug times, they're faster and they're more predictable and reliable. Okay, so onto the normal distribution. Are you feeling normal today? So in the previous sections, we have looked at discrete random variables. We have examined some probability distributions where the random variable x could take non-negative integer values, i.e. 0, 1, 2, 3, 4. That's what we mean by discrete random variables. It's not every value from 0 to 4. It's particular values like 0, 1, 2, 3, 4. So that's something we've looked at in the past. However, if you have, that was for binomial distributions. However, if you have a continuous random variable, as opposed to a discrete random variable, x can take on any value. So it could be 0.00052339, not just 0, 1, 2, 3, 4. The normal distribution is the most important distribution for a continuous random variable. So binomials more so for a discrete random variable, normal distributions for a continuous random variable. The normal distribution lies at the heart of statistics. Many naturally occurring phenomena have a distribution that is normal or approximately normal, such as heights of people, like the lengths of centipedes, heights of trees. The majority of them, so the mean would be kind of situated at the center. And you think of the area underneath as being the population. So of all the humans, most people are kind of average height. So that's why, like a little bit like out either side of the mean, there is most of the population exists within a tiny amount plus or minus from the mean. There's only a tiny amount of people are really short, tiny amount of people are really tall. Most people are average, so that's why there's a big area in the average around the mean. So many naturally occurring phenomena have a distribution that is normal or approximately normal, such as the chest sizes of English males. The distribution, most of them would be average, some are really large, some are really small. The distribution of errors in many manufacturing processes. The length of adult female tiger sharks, so most are around the average, and some are really only tiny amount really big, tiny amount really small. The length of cilia on a cell. Scores on tests taken by a large population. So as I said, when your exam results kind of are all calculated, they work out who gets 1, 2, 3, 4, 5, 6, 7 based on something similar to a normal distribution. In fact, I think they do a double normal distribution in IB. But it's generally following the idea of normal distribution, where only a tiny amount can get 7s, tiny amount will get 1s. Most people will get around 3, 4, or 5. Okay, yep. So that's what they assume. It's because examination boards tend to assume that human ability is more reliable than examiners writing a similar level test every year. And so to be able to use a normal distribution, though, there has to be a huge sample of students taking the same exam, like there is for IB. Scores on tests taken by a large population, that's important, has to be taken by a large population for you to justify using the normal distribution. Repeated measurements of the same quantity, yields of corn, wheat, etc. Scores on tests, yields of corn, and so on. So if X is normally distributed, then its probability density function can be given by this. So this is a pretty unusual looking equation. That's understandable. So probability density function. So you've seen things like, so you've got pi, you've got e for exponential in there, you've got mu, for the mean, you've got the standard deviation or variance, that kind of thing. Pretty complicated looking thing. So this probability density function represents a family of bell-shaped curves. These curves are all symmetrical around the vertical line, mu. So when we talk about the mean in the normal distribution, instead of using x with a line on it, we tend to use mu. So mu tends to mean, when we talk about the normal distribution, that means the mean, but when we're referring to the normal distribution. So we use mu to represent the mean. Each member of the family is specified by the parameters mu, the mean, and sigma, the standard deviation. So we've got mu, the mean, sigma, the standard deviation, and we've got pi, and we've got e. From negative infinity to positive infinity. That's 1 over blah, blah, e to the power of this thing. Pretty complicated. A normal distribution is a continuous distribution, so defined by 2 parameters, the mean and the variance. Because remember, the variance is the standard deviation squared. So remember, variance is the same as standard deviation squared. Because of the symmetrical shape of the normal curve, the mean is equal to the mode and the median. So this is interesting. So in a standard normal curve, the mean is equal to the mode and the median. So here's where the mean would be. It kind of splits the normal distribution in two. Normal distribution has a bell-shaped curve. Okay, so the normal distribution, so remember when we were saying x is distributed binomially, now we'd say x is distributed normally with a mean of mu and a variance of sigma squared. So that's a notation we use for the normal distribution. Whereas for binomial, we'd go x is approximately b, binomially distributed. You'd have n for the number of experiments and p for the probability of success. So instead, it's n is approximately normally distributed, a mean of mu and a variance of sigma squared. So to indicate that the continuous random variable x is normally distributed with a mean of mu and a variance of the standard deviation squared, sigma squared. The standard, this is important, standard normal distribution, by definition, has a mean mu of 0 and a variance of 1. That's what we call a standard normal distribution. It's got a mean of 0 and a variance of 1. In this case, the random variable is called z. So basically meaning that the x-axis here, it's just got the symbol z. The standard normal distribution has a mean of 0 and a variance of 1. So hence probably write n 0, 1. Moving along. Note that by definition, the area under the curve is 1. And do you know why? It's because, remember, all probabilities must all add up to 1. So probabilities must all add up to 1. So what do you think the area under the normal distribution represents? That's right, it represents a probability. So if this entire area under the curve here is 1, representing the probability, what would be the area to the left of the mean? That's right, it would be 0.5 because it splits it in half. What would be the area to the right of the mean? That's right, it would be 0.5 as well, because the mean splits the normal distribution in half. Now, to use your GDC to find the shaded area under the curve, you'll be given the z value, or you can just read it off the graph, off the scale, off the bottom of the curve. So on the GDC, just pointing out, I'll mime again, you would go second vase, because see that opens up distribution, second vase, and instead of binomial, you'd be selecting normal CDF. So second vase, select normal CDF, it'll be one of the earliest ones to pop up. And then, now you enter the lower bound and the upper bound. As you cannot enter in negative infinity into the GDC, you instead enter in a very low value, like -1 E99. Okay, so just put on Earth what I mean by this. So you'd go second vase, normal CDF, and notice I want you to tell you the lower and the upper bound. So see, this is the area. So this is the area here, and by the z values, I mean the values of the x-axis, the bottom axis here, the horizontal axis. So second vase, the lower bound is obviously all the way, goes on to negative infinity. The upper bound would be where does it stop here. So it doesn't go all the way up to positive infinity, it just stops here at 0.23. So the upper bound would be 0.23. And here, as we said, there's no way to enter in the term negative or the number negative infinity in the calculator. But you can put in a very low value like -1 E99. That means -1 times 10 to the power of 99. Sorry, it was -1 E99. Yep. Okay, so sorry, I'll just do this so you can see it up on the board. Okay, so that's what, so when you go second vase, normal CDF, this is what pops up, lower, upper, mu is 0 for the standard normal curve, and it is for this one too, as you can see, and the variance is 1. So find the area under a standard normal curve, 1. So because according to the standard normal curve, mean is 0 and the variance is 1. So therefore the standard deviation is 1. So that's why those are there. We need to put in the lower, so you put in -1 E99, the upper is 0.23. To put in this -1 E99, you make the E by pressing the EE button. So can you see the EE button on here? It's going to probably help to see on the version I've got because it's a little bit bright. Have a look around and see if you can find it. There's an EE button on your calculator. Can you see it? That's right, it's there. So you'd put in -1, and then to select EE, because it's in blue, you'd go second, comma. You'd select the EE, and then you just type in 99. And that's how you make this. -1 times 10 to the power of 99. So that just means a really, 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 really low negative number, very close to negative infinity. And then you press select paste, and it will give you the answer. So the area under this curve is 0.591. So the probability, another way of thinking of the area under the curve, it represents a probability. So the probability of something being between negative infinity, or basically the probability of something being less than 0.23 is 0.591. Makes sense according to the shape of the curve, because remember, to the left of the mean, here's the mean, mu, so to the left of the mean it should be 0.5. So it makes sense that because this falls slightly to the right of the mean at 0.23, it should be slightly bigger than 0.5. So 0.591 is that area there. So use your GDC to find each of the shaded areas under the standard normal curve. So it's a standard normal curve because you've got a mean of 1 and a variance of 1 curve shown. So how would you do that on your calculator? So you've got to think, what's the lower bound, what's the upper bound? So remember, you would press, you'd go normal, you'd go second vase, there's my fake calculator, you go second vase, select normal CDF, and then you put in your lower bound and your upper bound, and so on. So for this one, what would be the lower bound? The lower bound would be negative infinity, which you put in as negative 1e99. The upper bound would be 2.55, and mean is still 1 and sigma is still 1. So mean is still 0 and sigma is still 1. What would you get? Hopefully you get a similar answer to this. So when you put in 2.55 as the upper bound, the area is 0.99461. It might seem like that's really close to 1, so basically they just haven't drawn this to scale. So really it'd be probably more so like around here, because then it would be most, because remember the whole thing's 1. But they've intentionally not drawn it to scale for you. Same thing for this one. Now it's go second vase, normal CDF, and then the lower bound would be negative 1.2. The upper bound would be positive, so 1e99. So you'd put in 1e99 as your upper bound for this one. Not negative 1e9, because that's negative infinity. Positive infinity is 1e99. So then you would get, you don't need to write this is fine, leave that off, but what's important is 0.8849. These are kind of unrounded answers. Okay, so something like this one, so area to the left, it's from the lower bound, so go second vase, normal CDF, lower bound is negative 1e99, and the upper bound, what would the upper bound be? Upper bound would be negative 1.5. And then you should hopefully get that. Make sure you're trying this on the calculator first. Now try to do these ones. Notice this one's a nice easy one because second vase normal CDF, lower bound is 0.7, upper bound is 1.23. And then you should hopefully get this answer as being that area. Makes sense because it's less than 0.5. Same with this one, it makes sense. If it was more than 0.5, you know something would be wrong. This one, if it was less than 0.5, you'd know something would be wrong because 0.5 is this area here, so it's got to be bigger. And remember, mean is still 0, sigma is still 1. And here's normal second vase normal CDF. Lower bound is negative 1.3, upper bound is 0.62. Plug it in the calculator, you should get this number. So it's fine if you just write your answers, you don't need to write this stuff here. Okay, moving along. What if instead we gave you the area under the curve and they want you to find this Z value here, like the upper bound or the lower bound? So that's still possible. Okay, so on the GDC, you would go, so to do the inverse, it's basically like the inverse step of normal CDF. So if you remember, basically you go second vase, instead of selecting normal CDF, you would do the inverse step because it's finding the inverse of the normal step that we would normally do. Second vase, inverse norm. And then just enter in the area that they tell you for the calculate that is under the curve. So if they tell you that the probability is 0.9176 or the area under the curve is 0.9176, same thing, just enter in that area and it will. So see it, I just asked you for the area, asks you for the mean and the standard deviation. So you would enter in those and select paste. And here they tell you, oops, so we've just put in, so in the calculator it goes second vase, inverse norm, you put in the area that they give you in the question or the probability, the mean, standard deviation, and paste. The Z value is 1.39. It's good, it makes sense because the Z value you know should be up here somewhere, so it's got to be greater than 0. And according to this it's between 1 and 2, so you know something's right. So notice that the calculator always gives you the upper bound. It doesn't give you the lower bound, it just gives you the upper bound. So the calculator, just to make life easier, they give you the upper bound only. So what would happen if they instead wanted you to find the lower bound? So that's pretty easy, you just need to do a calculation first. So basically, if this little area here is 0.5, and they want you to find the Z value, the lower bound, then use this area instead, and then consider Z to be the upper bound. So what needs to go into the calculator is the area to the left. The area to the left of the z-value has to be what goes in the calculator. Remember, by definition, the area under a normal distribution equals 1. So you could work out this area by doing 1 minus that blue area. So 1 minus 0.05 is 0.95. So you would just put in the area as being 0.95, and the calculator will give you the z-value. So when the area is to the right instead, just instead find the area to the left by doing 1 minus the area to the right. So, by the way, that's a typo. It should say 1 minus 0.05. Feel free to fix that on your page, because yours says 1 minus 0.5 by mistake. It should be 1 minus 0.05. And the answer is correct though, it's 0.95. So pop in the area as being 0.95, the mean standard deviation. The z-value is 1.64, which makes sense as well for here. 1.64 is around about here. It's always good to be nice and critical. So now do some practice ones. Try it for yourself. Feel free to pause and try these yourself. Use your GDC to find each of the values of A. So here, notice they're telling you the area under the curve. They're telling you the probability. Here, they've given us the area to the left, so life's good. Just pop it in the calculator. Go second vase, inverse norm. So you don't need to write this step, but basically just reminding you that you're using second vase, inverse norm. And you'd put in 0.877 as the area. And the mean is still 0, and the standard deviation is still 1, because it's a standard curve. We should hopefully get 1.16, which makes sense. Here, they've got the area to the left. So they've given you the area to the right, sorry. So you're going to have to enter in the area to the left. So if that's 0.17, the area to the left will be, I think I've got a typo here, inverse norm 0.95. So this is wrong. So 0.95, I think I must have just left it in from the previous slide, sorry. So what should this be instead? This should be 1 minus 0.17. What's 1 minus 0.17? That's right, it's 0.83. So it should be inverse norm, second vase, inverse norm, put in the area as 0.83. This is why it's really important that you do listen to me while keep the audio up while you're watching these videos, or else you'll still have the same mistakes there and you'll get confused. So A equals 0.95, that might have been where I was getting my error from. So the area is 0.95, which makes sense because it's got to be more than 0.5. It looks like it's less than 0.95, but they've just intentionally not drawn it to scale to put you off. Same thing here. So this is interesting. They want you to work out the value of A. They want you to work out what negative A is. So what's the negative of A? So what you could think of is, so you know this area here is 0.162. So instead you could think of positive A as being over here. So if 0 is here, if that's negative A, positive A would be over here, in which case the area to the left would be 0.62. So think of what positive A would be. So positive A would be over here, and the area to the left would have been 0.62. So that's why we've just got to work out, or alternatively, you could also just work out what negative A is. So think of that as 1 minus 0.62 is 0.38, so this area here is 0.38. So work out what negative A is. So negative A would be negative 0.305, and so on. So basically, I get you, because they're saying negative A, they want to know what positive A would be. So that's why we don't need to switch it around. So positive A would be here, but yeah, they want to work out what negative A is. So it would be negative 0.305, because if we know it needs to be a negative number, so we know it needs to be a negative number because it's to the left of 0, and so on. So A must be equal to a negative number because it's got to be, this value, Z value here, has to be a negative. So you put in inverse norm 0.38. So notice this one's an interesting one. Notice it's symmetrical. So we've got negative A here, we've got 0.44. We've got negative A here, we've got positive A here. So it's symmetrical. So what do you know? If that's 0.44, what must this little half area be? So this entire thing's 0.44. What must this little area be? That's right, it must be 0.22. So work out A by using the area. So you know this little bit's 0.22. You know this whole thing here is 0.5. So instead, to work out A, the area to the left of A, would be 0.72, because the area to the left of A would be this 0.22 plus this entire 0.5 section. So go inverse norm 0.72 and you'll get your answer. Inverse norm 0.72, you'll get A equals 0.583. So these things are just pointing out that this bit here is 0.5, this bit here is 0.22. And then inverse norm that entire thing, which is 0.72, A is 0.583, which makes sense. It's got to be a value more than 0. Moving right along. So what's the point of finding the area under the curve? The area under the normal curve in real life represents a probability. So if Z is approximately normally distributed with mean of 0 and a variance of 1 or standard deviation of 1, then this symbol here represents the area or the probability. That funny symbol you might have seen earlier represents the area probability of A, represents a probability that Z is less than A. So given that Z is approximately normally distributed, well, it follows a standard normal curve, find each of these probabilities. So we know that mu is 0, sigma is 1. Probability that Z is less than 2.68. What does that mean in terms of a normal distribution? I do a quick sketch of the normal curve to see what that means. So they want to know, if they want to know a probability, they want to know the area under the curve. So that's why it's second bar's normal CDF, because they want the area under the curve if they want to know a probability. So if it's less than 2.68, and we know that the mean is 0, so it's got to be, 2.68 has got to be to the right of the mean. So it's got to be equal to 0.5 and more. So you go second bar's normal CDF. Remember, you're putting your lower bound as being negative 1E99, putting your upper bound as being 2.68. And you should hopefully get an area of 0.9963. So that area is 0.9963. So the probability that of a Z value less than 2.68 is 0.9963. So what could this be? They could be talking about heights, or they could be talking about someone's grade, or anything, like, the length of centipedes or something like that. That's what these things could represent in the real world. Find the probability that Z is greater than negative 1.41. So greater than meaning up here somewhere. So what would that mean if you were to sketch that? So notice that Z is greater than negative 1.41. So do your little standard normal curve. Mean is at 0. So negative 1.41 must be to the left of the mean. So, and probability that Z is greater than. So you go second bar's normal CDF. Lower bound is negative 1.41. Upper bound is 1E99. So you put in that, and you would hopefully get 0.9207, which is the area under that curve and the probability. So continue from the previous slide. Find the probability that the Z value is greater than 0.2 and less than 1.71. Notice that they don't have equals 2 signs on there. So do a sketch of that. So 0.2 is greater than the mean, so it'd be up here. 1.71 is, of course, even more greater than the mean. So they want to know the value between here. So you'd go second bar's normal CDF into your lower bound as being 0.2, your upper bound as being 1.71, and you would get 0.3771, which makes sense because it's got to be less than half. Find the probability that the absolute value of Z is less than 1.1. What on earth does that mean? So what it means is absolute value of Z, meaning that from negative 1.1 to positive 1.1. It's because absolute value means Z could have been negative 1.1 to positive 1.1 is less than 1.1. So less than meaning getting closer and closer to 0. So that's why it's not getting further out here. If it said greater than 1.1, it would be this area here and this area here. But it says less than 1.1, so it means these values, because they're closer to 0 if they're less than 1.1. So you'd go second bar's normal CDF. Lower bound is negative 1.1, upper bound is 1.1. Plug it in the calculator, and you would get an area of 0.7286. And continuing on. How can other probability distributions be transformed into the standard normal? So you can transform other probability distributions into the standard normal curve. You now know what to do with the standard normal distribution, but very few normal distributions in the real world will actually have a mean of 0. Like if you're talking about heights of trees or lengths of dogs, then chances are the mean is not really 0. But you can take their distributions and you can transform them into the normal curve. So very few normal distributions in the real world will have a mean of 0 and a standard deviation of 1. However, it's not difficult to transform any set of normal data into the standard normal curve. Let's show you how to do that. So suppose instead, like something that's probably more in the real world, you'd have a mean that's a positive value, a standard deviation that's kind of like more than 1 or less than 1, doesn't matter. Suppose that x is approximately normally distributed, the mean of mu, and a variance squared. What you could do is to center the distribution, so basically to make it with a mean of 0, which is what the standard normal curve has to have, you would just easily just take the mean and you would subtract the mean, and then that would give you a standard 0. So subtract mu to center the distribution on 0, that's what you would do, and divide by the standard deviation to give a standard deviation of 1. So because standard deviation, if your standard deviation was 2.4, 2.4 divided by 2.4 equals 1. So that's why we need to subtract the mean, and divide by the standard deviation. But there's a little formula in your formula booklet to remind you of this. So don't worry, it's given in your formula booklet. C, suppose the random variable x is normally distributed. In such cases, this is how you would transform it. Z value equals whatever the real value of x was in the real world, minus the mean to center it back to 0, and divide by the standard deviation to give it a standard deviation of 0. So this is given in your formula booklet though, but the previous slide is just trying to explain to you why we do that. So we subtract the mean to center it back to 0, so we subtract the mean, so everything shifts back to 0, and we divide by the standard deviation so that it kind of ends up with a standard deviation of 1. So given in your formula booklet. This formula is used to give a normal distribution with a mean of 0 and a standard deviation of 1. The normal distribution curve, you write z is approximately normally distributed with a mean of 0 and a standard deviation of 1. The transformation combines variance of 1. The transformation combines the translation of subtracting the mu and a change of scale, dividing by sigma. Given that the random variable x is normally distributed with a mean of 2, and remember this is the variance, is 3 squared, so the standard deviation is 3. So the mean is 2 and the standard deviation is 3. They'll tend to have the square there. Determine the probability that x is less than 3. Okay, so they want to know the area under the curve. But what we need to do first of all is transform the z value first into the standard normal curve. So 3 in standard units is, so you go z equals the x value, because remember we're using this formula back here, x minus mu over sigma. We're transforming the z value first before putting it into the calculator. So I've got to transform it into the standard normal curve first. So go z equals the x value minus the mu minus the mean, divide by sigma, the standard deviation, which is 3. 3 minus 2 is 1, and 3. So instead, if you're going to put in the calculator, you're going to go second bar's normal CDF. We're basically finding the probability that z is less than a third instead of x is less than 3. Because we've transformed that x value into a z value. Z represents an x value for a standard normal curve. So basically, if they want the probability, they want the area under the curve. So they want to know, and less than that, so it's to the left of it. And we've got 0 here, so 0.3 must be up here somewhere. So you go second vase, normal CDF. Lower bound is negative 1e99. Upper bound is 0.3 recurring, or you can do 1/3, because that's what 0.3 recurring is. Don't do 0.3, because that's different. And you get 0.6306. Again, makes sense because 0.6306, it's more than half of the standard normal curve. Here's another one. Given that the random variable x is approximately normally distributed with a mean mu of 6 and a standard deviation of 2, determine the probability that x is greater than 10. So just reminding you here, 2 squared is a variance, so the standard deviation is 2. So sigma is 2, and 6 is the mu, and so on. So what you'll do is, sorry, I just got to turn the page onto my notes. So what you do is transform. So you would transform this first using that formula. Z equals x minus mu over sigma. So Z equals the x value, 10. Transform it to the standard normal curve first. 10 minus the mu, 6, divided by 2. 10 minus 6 is 4. 4 divided by 2 is 2. So basically what we're trying to find is probability that Z is greater than 2, because we've transformed it now into the standard normal curve, so we can use probability Z is greater than 2. So we go second vase normal CDF. Second vase normal CDF. The lower bound is 2 because Z is greater than, so it's greater than this time. Lower bound is 2, the upper bound is 1e99, positive 1e99. Remember, because we've transformed it into the standard normal curve, the mean, we put in the mean as being 0, and the other thing is being 1. So 0.0228, because it's less than 0.5, makes sense. Here's another one. Almost there. So given that the random variable x is normally distributed with a mean of 20 and a standard deviation of 4, determine the probability that x is between 16 and 21. So we've got to transform this one, and then we've got to transform this one. So using your z equals x minus mu over sigma, which is in the formula booklet. So 16 in standard units would be 16 minus the mean, divided by the sigma. 16 minus 20, that's 4. 16 minus 20 is negative 4. Negative 4 divided by 4 is negative 1. So we've got negative 1 here. 21, we're now going to transform. 21 minus the mean, divided by sigma, the standard deviation. 21 minus 20 is 1. 1 divided by 4 is 0.25. So find the probability that x is between 16 and 21. It's like saying what's the probability that z for the standard normal curve is between negative 1 and 0.25. So between negative 1 and 0.25, so negative 1 would be to the left of the mean, 0.25 would be to the right of the mean. So go second bar is normal CDF, put in negative 1 as a lower bound, 0.25 is the upper bound, mean is 0, and sigma is 1. You get 0.44 as being the probability. Here's another one. Given that x is approximately normally distributed with a mean of negative 1 and a sigma, a variance of 3 squared, or a standard deviation of 3, determine the probability that the absolute value of x is greater than 2. So it's not less than 2 this time, so it's not between 2 and 2, it's on the outside of 2 and negative 2. So first of all, transform them first, and I'll show you what that means. So transform negative 2, transform negative 2 first, and then we'll transform positive 2. Negative 2 in standard units is z is x minus, so negative 2 from here, x minus the mean divided by sigma. So minus 2 minus negative 1 is like minus 2 plus 1, which is minus 1. Minus 1 divided by 3 is minus a third. And then positive 2 in standard units is 2 minus the mean of negative 1 divided by sigma. 2 minus negative 1 is 3. 3 divided by 3 is 1. So now we're trying to work out probability that z, and because it's greater than 2, I'll try to draw in the thing, they mean outside of these limits. So using the standard normal curve, if it was less than, then it would be this value in between, like we said, because less than means getting closer to 0. But greater than means outside the limit. So that's interesting. They want to know probability of this and the probability of this. So you could work them out separately and add them together. So you could do second vase normal CDF. Lower bound is negative 1e99, upper bound is negative a third. work out that. Then you could also do second vase normal CDF, lower bound is 1, upper bound is 1E99, then add those two together. Alternatively, you could work out this missing bit here and then do 1 minus that. So this one here, by the way, this area here when I did it the other way, came up with this. And this area here, sorry, wrong ones, came up with that. Oops, go back to here. And then you end up with that, and then you end up with that. Yep, so sorry, this one here ended up being this one, and this one here ended up being that one. And you add that one to that one, and you get this value. I think there was a mistake in the previous answers. Alternatively, you could do, just do 1 minus this little area here. So you could work out this one by going second vase normal CDF, lower bounds -1/3, upper bounds 1, and work out that answer, and then do 1 minus that, because the area under the whole curve is 1. That would work too. Here's our last one. So almost at the last one. No, second last one. Given that x is approximately normally distributed with a mean of 10 and a standard deviation of 3, determine x where the probability of x is greater than x equals 0.08. So it's an inverse norm problem. They've told us the area under the curve, and they want us to now work out the z value. Well, they want you to work out x. So what you could do, so to do inverse norm, we need the area to the left, remember? So they've told us that the area, that probability that x is greater than x is 0.08. So they've told us the area to the right. So remember, in the calculator, we need to give them the area to the left when we're doing inverse norm. So that's the area to the right because it's saying probability that x is greater than x. This, but to the left would be the probability that x is less than x, is this area. So to work this out, you just do 1 minus 0.08. So 1 minus 0.08 is 0.92. So this red area here is 0.92, and when doing inverse norm, that's what needs to go into the calculator. So you go second vase inverse norm, tell it that the area is 0.92, and then you'll get 1.4053. In the standard normal curve, 1.4053 would be that particular value. But therefore, and then you need to transform that using the standard normal curve transformation formula. Z equals x minus mu over sigma. So 1.4053, x in standard units as a z value would be, so the z value, sorry, is 1.4053. We've got the z value. We want to work out the x value because they said find x. So the z value is 1.4053. Mean is 10 and standard deviation is 3. So and then you need to solve for x in this case. So multiplied by 3, add 10, you would get 14.2 rounded to 366. A bit complicated. Okay, so one little final thought. How are the standard normal distribution and the standard deviation related? So this is interesting. For a normal distribution with a mean mu and a standard deviation of sigma, the proportional breakdown of where the random variable could lie is given alongside. So in general, with a standard normal curve, you've always got the mean, mu, in the center. In general, the mean plus 1 standard deviation and the mean minus 1 standard deviation, by definition, approximately 68% of the data. So imagine that we were talking about all the students sitting in the IB. So they're saying approximately, if you were to do a basic normal distribution for that, they assume 68% of the people fall between the mean plus 1 standard deviation, the mean minus 1 standard deviation is about 68% of the population. The mean plus 2 standard deviations and the mean minus 2 standard deviations is kind of a bigger amount. It would be that amount plus that one, plus that one, plus that one, and so on. So notice that approximately, back to here, 2 times 34.13, so about 68.26 of the values lie between plus and minus 1 standard deviation of the mean. So moving out to 2 standard deviations from the mean plus 2, the mean minus 2 standard deviations, approximately 95.44%. If you do this one plus this one plus this one plus this one, you get about 95.44% of the population fall between plus or minus 2 standard deviations of the mean. and approximately almost the entire amount, but not quite. So approximately 99.74% of the values lie between plus and minus 3 standard deviations of the mean. So that would be the 0.13, sorry, the 2.15 plus the 13.49 plus here, not the plus 0.13, but from these values to here, adds up to 99.74. So the 0.13 is outside of the mean plus or minus 3 standard deviations. So that's a general kind of basic breakdown of the standard normal distribution. By definition, we call it in Australia, we call it the 68, 95, 99. 0.5% rule, but every textbook has different percentages depending on which course you're following. So our one kind of follows this one. Okay, and that's the end of the lesson. If it was confusing, that's fair enough. You probably just want to do quite a lot of practice problems. Make sure you practice a lot using your calculator too. That's really important in the exam.